7. In what smallest whole number ratio must nitrogen and oxygen atoms combine to make dinitrogen tetroxide? Dinitrogen tetroxide, right? Well, the ratio is 2 to 4. 2 nitrogens to 4 oxygen. What's the mole ratio of elements in this compound? 2 moles of nitrogen to every 4 moles of oxygen, or 1 mole of nitrogen for every 2 mole of oxygen, right? All right, 429. How many moles of tantalum atoms correspond to 1.56 times 10 to the 21 atoms of tantalum? How many moles of tantalum? 1.56. So we want moles of tantalum. We want moles of tantalum, and we're going to start with atoms of tantalum. 1.56 times 10 to the 21 atoms. 1.56 times 10 to the 21 atoms of tantalum. All right, so 1.56 times 10 to the 21 atoms. How many moles of atoms is that? Because if we know how many moles of atoms that is, then we know how many moles of the material we have. So 6.02 times 10 to the 23rd atoms of tantalum. That's 1 mole of tantalum. So therefore, we should be able to take 1.56 times 10 to the 21 divided by 6.02 times 10 to the 23rd, and that should tell us how many moles of tantalum atoms there are. Let me get my calculator. 1.56 times 10 to the 21. 1.56. Okay, so just in case you don't know how to do this, right? 1.56 times 10 to the 21. Start over. 1.56. Second, this comma button here, EE, that's times 10 to the, and then you put the number in, times 10 to the 21, and then we're going to divide that by 6.02 times 10 to the 23rd. All right, so that's going to be 0.00259, and we have 3 significant figures. That's 0.00259 sucrose, table sugar, has the formula C12H22O11. In the compound, what's the atom ratio of carbon to hydrogen? There's 12 carbons to 22 hydrogen. All right, so that's 6 to 11. 6 carbons for every 11 hydrogens. Right? Divide that by 2. Divide that by 2. All right, so that's the atom ratio of carbon to hydrogen. B, what's the mole ratio of carbon to oxygen? Well, there's 12 carbons, 12 moles of carbon to every 11 moles of oxygen. So this number now means atoms in the molecule, but it also can be moles in any size unit. Moles per molecule, moles per unit, right? All right, C, atom ratio of hydrogen to oxygen, 2 to 1, twice as many hydrogen as oxygen. Mole ratio of hydrogen to oxygen, again, that's D, mole ratio of hydrogen to oxygen, that's going to be 2 to 1 as well. All right, 433. Well, that was 431. And now we're on to 433. 433. How many moles of bismuth atoms are needed to combine with 1.58 moles of oxygen atoms to make bismuth oxide? We want to know moles of bismuth. And we've been told that we have 1.58 moles of oxygen. 1.58 moles of oxygen. All right. How many moles of bismuth? Well, we need moles of bismuth on top and moles of oxygen on the bottom. So we can know, based on the kind of compound we're forming, which is Bi2O3, bismuth oxide. All right, so let's see. All right, BiO2, let's see, Bi2O3. Well, we know in one of these compounds there are 2 bismuths, moles of bismuth, for every 3 moles of oxygen. So if we take 1.58, multiply by 2, divided by 3. So I'm getting 1.05 moles of bismuth. Okay, and that is 4.33. How many moles of chromium are in 2.16 moles of Cr2O3? 2.16 moles of Cr2O3. And the question is moles of chromium, right? How many moles of chromium are in 2.16 moles of Cr2O3? Well, we need moles of chromium up here, and we want to get moles of Cr2O3 are down here, right? So for every 1 mole of Cr2O3, there's 2 moles of chromium. Therefore, 2.16 times 2, and that should be how many moles of chromium. Let me get my calculator here. Moles of chromium in 2.16 moles of Cr2O3. So we got 2.16 times 2, 4.32. 4.32 moles of chromium. So that's number 435. 437. 437 says aluminum sulfate, Al2SO43, is a compound used in sewage water treatment plants. Construct a pair of conversion factors that relate moles of aluminum to moles of sulfur for this compound. Al2SO43. Al2SO43. Aluminum sulfate. Okay, aluminum, we can look on the periodic table and know that it's an A. It's just a quick review. I'm just doing this for review. Al plus 3 ion, right? Therefore, we're reminded that the sulfate, SO4, has a 2 minus charge on it, okay? So, what's some conversion factors? Well, for every 2 moles of aluminum, there are 3 moles of sulfate. 2 moles of aluminum, there are 3 sulfates, right? So, if you had 2 aluminums, for every 1 aluminum sulfate, there's 2 aluminums and 3 sulfates. That can be one conversion factor. What are we supposed to do? Construct a pair of conversion factors that relate moles of aluminum to moles of sulfur for this compound. Another conversion factor can be for every 1 Al2SO43, there are 3 sulfurs. Right, so that's another example of a conversion factor. B, construct a pair of conversion factors that relate mole of sulfur to moles of aluminum sulfate. Oh, sorry, that's the conversion factor there. This is the first one here. How many moles of aluminum are in a sample of this compound if the sample contains 0.9 moles of sulfur? The question, how many moles of aluminum are in a compound that contains 0.9 moles of sulfur, 0.9 moles of sulfur. Therefore, there's 3 sulfur. For every 3 sulfurs, there's 2 aluminums. So if I have 0.9 moles of sulfur in this compound, the ratio of aluminum sulfur to aluminum is 3 to 2. So I could take 0.9 divided by 3, multiply it by 2, and that's C. So that's here. 0.9 times 2 divided by 3. 0.6 moles of sulfur. And this is 437. 0.6 moles, of aluminum. 0.6 moles of aluminum. Good. D, part D, how many moles of sulfur are in 1.16 moles of aluminum sulfate? So how many moles of sulfur now is what they're asking? 1.16 moles of aluminum sulfate. Al2SO43. Well, for every 1 mole of aluminum sulfate, for every one of those, we have 3 sulfurs. Therefore, it's 1.16 times 3, right? And that's the question, right? How many moles of sulfur are in that many 1.16 moles of aluminum sulfate? So 1.16 times 3. So that's 3.48 moles of aluminum. All right, that's 437A through D. 439, how many moles of hydrogen gas and nitrogen gas can be formed by the decomposition of 0.145 moles of ammonia? .145 moles of NH3. How many moles of H2? How many moles of N2? 0.145 moles of NH3. Right? Well, for every 1 mole of ammonia, I can get, we're looking for moles of nitrogen. I start on the second one first. For every 1 mole of ammonia, I can get 1 nitrogen. Right? There's 1 nitrogen. There's 1 mole of nitrogen for every 1 mole of ammonia. This is how many moles of ammonia we have. And for every 1 mole of nitrogen, I can get 1/2 a mole of N2 gas, nitrogen gas, right? So 0.145, 1 to 1 here, times 1/2, and that's how much nitrogen gas I can get, right? 0.145 divided by 2, and that's 0.0725. That's how many moles of nitrogen gas I could get. On this one here, for every 1 mole of NH3, there's 3 hydrogens. And for every 3 hydrogens, that can give me 1.5 H2s, right? So 0.145 times 3 divided by 3 times 1.5, right? So it's just 0.145 times 3 divided by 3, that cancels each other out, so times 1.5. And we get 0.2175 moles of hydrogen gas. Let's double check those. Oh, sorry, that was 439. How many moles of uranium fluoride would have to decompose to provide enough fluorine to prepare 1.25 moles of CF4, carbon tetrafluoride? Assume sufficient carbon is available. Okay, so to prepare 1.25 moles of CF4. 1.25 moles of CF4, right? And the question is, how many moles of uranium fluoride, which is UF6? UF6, all right? So, all right. Nose is right. 1.25 moles of CF4. How many moles of UF6, uranium fluoride, is it going to require? Well, for every 1 mole of CF4, let's see, how many moles of UF6 would we have to decompose to provide enough fluorine? So we're just looking for the fluorine. So there's 4 moles of fluorine. All right? So if we want to make that much stuff, we need to start with 4 moles of fluorine. And if we're going to get the 4 moles of fluorine from here, then we need to, there's required 6 moles of fluorine for every UF6. So if we take 1.25, so this is moles of CF4, moles of fluorine, and moles of uranium fluoride. So 1.25 times 4 divided by 6. 1.25 times 4 divided by 6, 0.833. 0.833 moles of fluorine. All right, 441. 0.833. Good. 443. How many atoms of carbon are combined with 4.13 moles of hydrogen atoms in a sample of the compound propane? C3H8. How many atoms of carbon? How many atoms of carbon? Okay. So we want atoms of carbon. That's what we're looking for, right? How many atoms of carbon are combined with 4.13 moles of hydrogen atoms? 4.13 moles of hydrogen. 4.13 moles of hydrogen atoms in a sample of propane. So in the sample of propane, you have C3H8. We want moles of hydrogen atoms down here. And there's 8 moles of hydrogen atoms, C3H8. 8 moles of hydrogen atoms for every 3 moles of carbon, right? 3:8 ratio. So now we're in moles of carbon. So that's it. They want to know the number of atoms of carbon, or they want moles of atoms. So we're going to need 4.13 times 3 divided by 8. And that's how many moles of carbon atoms we're going to need. 1.55 moles of carbon atoms. Now, if they actually want how many atoms are required, right, then we're going to have to take that 1.55 moles of carbon and say how many atoms of carbon. I'm not sure what they're asking, because it sounds like they're asking for atoms of carbon, but then they express this in terms of moles of atoms, right? So is it moles of atoms that they want the answer in, or in numbers of atoms? It doesn't matter, it's the same thing. But here, if we want to go to atoms of carbon, how many moles of carbon are in an atom of carbon? Well, for every 1 mole, there's 6.022 times 10 to the 23rd, right? Let me rewrite that. Every 1 mole of carbon, 6.02 times 10 to the 23rd atoms of carbon. So 4.13 times 3 divided by 8, if you want to go to atoms, times 6.02 times 10 to the 23rd, because that's how many atoms there are in every mole. If you don't, then you just stop at 1.55. So let's see, what did they do? 443, they went to atoms. So we're going to have to put atoms as well. So we take 1.55, multiply by this, or just 4.13 times 3 divided by 8 times 6.02 times 10 to the 23rd. So it's 9.32 times 10 to the 23rd atoms of carbon. You do that one right? 43? Yeah. Okay. All right, what's next? 445. What is the total number of carbon, hydrogen, and oxygen atoms in 2.60 moles of glucose? .45, right? What is the total number of CH and O atoms in 0.260 moles of C6H12O6? Sum of all the carbon, hydrogen, and oxygen atoms in 0.260 moles of glucose. Then we want moles of that stuff, right? What's the total number of, no, not moles of this stuff, total number of atoms. Atoms of carbon, hydrogen, and oxygen all combined. All right, this is how many moles of this. So we have, for every 1 mole of this, 1 mole of C6H12O6, there's 24, 6 plus 12 plus 6, 24 moles of CH and O atoms. And for every 1 mole of CH and O atoms, there's 6.02 times 10 to the 23rd CH&O atoms. All right, so 0.26 times 24 times 6.02 times 10 to the 23rd. So I'm getting 3.76 times 10 to the 24th. 445, is that right? All right, good. Let's see, 447. How many atoms are in 6 grams of carbon-12? How many atoms in 6 grams of carbon-12? 6 grams carbon-12 atoms of carbon. You need grams of carbon-12 on the bottom, moles of carbon-12 on top. So there's 12 grams of carbon-12 in every 1 mole of carbon-12. Therefore, we have a half a mole. Right? And now we're in moles of carbon. For every 1 mole of carbon, there's 6.02 times 10 to the 23rd atoms of carbon. Right? So 6 divided by 12 times 6.02 times 10 to the 23rd, which is half Avogadro's number, or 3.01. All right, let's see, that was 447. Okay, 447, 449. Determine the mass in grams of each of the following. 1.35 moles of iron. Determine the mass in grams. 1.35 moles of Fe. Well, for every 1 mole of Fe, how many grams of Fe are there? Well, we can look at the periodic table. It says that the atomic mass is 55.85. So there's 55.85 grams for every mole. So 1.35 times 55.85. 0.35 times 55.85. That's 75.398 or 40 or 75.4 grams of iron. 449, that was. Part B, though, says 24.5 moles of oxygen. How many grams of oxygen in 24.5 moles of oxygen? Is that oxygen atoms or oxygen gas? Just oxygen atoms. 24.5 moles. For every 1 mole of oxygen, there's 16 grams of oxygen. All right? You look on the periodic table to remember that. Oxygen, 16 grams per mole. That's the mass for every unit. Mass per mole. 24.5 times 16. .392 grams of oxygen. There's A and B. 0.876 moles of calcium. 0.876 moles of calcium. How many grams of calcium? Well, for every 1 mole of calcium, calcium has a mass of 40.08 grams of calcium. 40.08 times 0.876. 35.11 grams calcium. All right, 449. Now we're on to 451. Now I have something written in my book here. I think this might be one that has a problem. Wrong significant figures in the back. Okay. So this one has the wrong number of significant figures in the back, 451. Nanotechnology experiment requires 2 times 10 to the 12th atoms of potassium. What's the mass of this atom? Mass? So we want to know the grams of potassium. It requires 2 times 10 to the 12th atoms of potassium. All right, so 6.02 times 10 to the 23rd atoms of potassium is the same as 1 mole of potassium. And 1 mole of potassium, I know how many grams that is. I can look on the periodic table. Potassium, the bottom number, 39.10 grams for every mole. So if I take 2 times 10 to the 12th and divide by 6.02 times 10 to the 23rd, that will put me in moles of potassium, multiplied by 39.10. That will tell me the mass or grams. 2 times 10 to the 12th divided by 6.02 times 10 to the 23rd times 39.10. 1.3 times 10 to the minus 10. Very much. Let's see, that one has the wrong answer in the back of the book. Let's see what they have. 451. So they say 1.30 times 10 to the, so they have 3 significant figures, but the answer only has 1 significant figure. So it should only have 1. All right, 153. How many moles of nickel are in 17.7 grams of nickel? How many moles of nickel? 17.7 grams of nickel. All right, well, for every 1 mole of nickel, we can determine how many grams of nickel there are. That's what we want, right? We want to go from grams to mole. So just double check here. How many moles of nickel are in 17.7 grams of nickel? We can look for nickel and see that it's 58.69. 58.69 grams for every mole. So 17.7 divided by 58.69. That's 0.301 moles, or 302 if you round the right, moles of nickel. All right, that's 453. Now it's 455. Calculate the formula mass of each of the following to the maximum number of significant figures possible using the table of atomic masses inside the front cover. NaHCO3. NaHCO3. All right? One sodium. So you use the table of masses inside the front cover to find the masses, and what you're looking for is the what they call the formula mass, also known as the molar mass. And the molar mass, or the formula mass, is the grams that there are for every 1 mole. And I'm looking for my periodic table here. I'm just going to use my numbers that I have here. To do the maximum number of numbers possible, same thing. You just have to use the masses that they give you in the front cover of your atomic, on your periodic table there. So sodium, what do we got? 22.990. Hydrogen, 1.0079. Carbon, 12.011. Oxygen, 15.999. We have to multiply that by 3, right? So this is for sodium bicarbonate, correct? Number 55A, sodium bicarbonate, NaHCO3. Calculator. Just add them up. 22.990 plus 1.0079 plus 12.011 plus, and then we can put in parentheses here, 15.999 times 3. Okay? So I'm getting 84.059. 84.050059. And in terms of numbers of significant digits, it looks like I'm going to be limited to 3, so it's 0.006. But if you use different masses in your from the front cover, then you would get slightly different value as well. 455, 84.0066 is what they have. Okay, that's sodium carbonate. Next, ammonium carbonate. B, ammonium carbonate. NH4,2CO3. NH4,2CO3. Right? So we have NH4,2. So we have 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens. Right? Well, carbon, we have it up here, 12.11. 12.011. Nitrogen, 14.007. And we need 2 of those. 8 hydrogens, so 1.0079 times 8. And then 3 oxygens, 15.999 times 3. So I'm getting 96.085. 96.085. Good. This is for A, this is for B, these are the answers. All right. C, copper sulfate pentahydrate. CuSO4 5H2Os, right? Copper, the mass of copper is 63.546. Remember, those units are grams per mole, and that's why we can answer these problems this way. Just add them all up. Sulfur, 32.065. Okay, so we have 32.065 plus 1 copper, 63.546, plus 5 times 2, 10 hydrogens, right? So 10 1.0079s plus 5 oxygens. So that's 5 times 15.999. All right, so I'm getting 185.685. 185. Wait a second. What did I miss? Oh, I only added those 5 oxygens. I also have to add these 4 over here. So plus an additional 4 times 15.999. 249.681. That's it. 249.681. Good. So I added up 1 copper, 1 sulfur, 4 plus 5, 9 oxygen, and then 10 hydrogens. D, potassium dichromate. Well, you have to look on the table to determine what the dichromate ion is. Potassium has a +1 charge. We can look at the periodic table and see that it's going to form a +1 ion. And the dichromate ion is Cr2O7, and it has a -2 charge on it. Okay, so that's going to make this K2Cr2O7. Right? Does that make sense? What's the page number on that table so you can look it up? It's page 85 or something like that. 84. The dichromate ion, right. So it's on page 84. Okay? So K2Cr2O7 is what we want to find the molar mass of, or the formula mass. Okay? 2 potassiums, 2 chromates, and 7 oxygens. Well, I know this oxygen mass right here, 15.999, so I go 15.999 times 7. That's for all the oxygens, plus potassium is 39.096. 39.096 times 2 of those, right? Plus chromium. Chromium is 51.996. Plus 51.996 times, again, 2 of those. So I'm getting 249.177. 249.177. Double check. 249. What did I miss? 1847. 249.177. Oh. So pretty close. Looks like my values are slightly different than theirs, but that's all right. All right, that's D. What's E asking? Al2SO43. Aluminum. We're triple checking, right? Aluminum, 26.982 times 2. Sulfur, 3 sulfurs. 3 times sulfur, 32.065. 4 times 3, 12. Oxygen, 15.999. We add all these together, right? 26.982 times 2. 53.964. 3 times 32.065. 96.195. 12 times 115.999. 191.988. Well, there's my problem. What did I do? So it's 342.147. All right, let's see if that value is right. 342.151. So that's right. All right, good. Sorry about that. I had the multiplication sign wrong in my calculator. All right. So we're on to 457 now. Calculate the mass in grams of the following: 1.25 moles of calcium phosphate. 1.25 moles of calcium phosphate, PO4, 2. All right, so calcium phosphate, we want to know how many grams of calcium phosphate that is, right? We want to know how many grams. So we need to have a relationship between the moles of calcium phosphate and the grams of calcium phosphate. All right, so calcium. Each calcium has a mass of 40.1. So there's 3, so 40 times 3. Plus 2 phosphorus is 31 plus 31. Plus 8 oxygens. So I'm getting a mass of 310 grams per mole about. So 310 times 1.25, 387.5. 387.5. And that is for 457. Okay, they have 388, 3 significant figures. 388. Good. 388. Now, you might have noticed that when I determined the formula mass of that, I didn't use all the significant digits, right? I just took the first 3, all right? Because I saw that there was only 3 significant digits here, okay? And that might change your numbers slightly in terms of getting the absolute right value down to the last gram. But it's generally okay, and I'm not going to be a stickler with those last few digits, okay? I mean, we want it to be right, but you're not going to be off by any significant amount for the given problem. All right, 459. Oh wait, we're not done with 457. B, C, and D. So 0.625 millimoles of iron nitrate. 0.625 millimoles. 0.625 millimoles of iron nitrate. Fe, and it's iron 3 nitrate. So Fe plus 3 came together with nitrate, NO3 minus, right? So that means iron nitrate is going to be FeNO3. Okay? So FeNO3, that means we take 3 nitrogens, 14 times 3, plus plus 16 times 9. Right, 16 is the mass of oxygen, and there's 9 of them. Plus 1 iron, and 1 iron was 55.8. So I'm getting 241.8. So, sorry, I kind of jumped the gun. So there's 241.8 grams for every mole of FeNO3, iron nitrate. Okay? And we want to know how many grams of FeNO3, iron nitrate, there are in this many millimoles. Okay? Millimoles, well, for every 1 millimole, well, not 1, every 1,000 millimoles of iron nitrate, we have 1 mole of iron nitrate. Okay? And then for every 1 mole of iron nitrate, we have 241.8 grams of iron nitrate. So 0.625 divided by 1,000 times 241.8. So I'm getting 0.151. 7B.151. Good. Got it. Grams of iron nitrate. That was B, 455C, or 457C, 0.6 micromoles of CH for C4H10. 0.6 micromoles of C4H10. C4H10, you guys know what that is? Should be C4, 4 carbons, that's bute. It follows this 2N plus 2 rule, so it's butane, right? It's a form of butane, if not butane, okay? So this is the CnH2n plus 2 rule, right? 8 times 2, 4 times 2 is 8, plus 2 is 10. So it could be this, right? Carbon, 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 with hydrogens all around, right? That's butane. All right, so if we have that many moles, how many grams of butane? Well, we'll call it C4H10. So this is how we draw it, and an even simpler, easier way to draw it would be 1, 2, 3, 4, just like that, right? But we don't know that it's like that. It could be like this, 1, 2, 3, and then there could be a fourth one like that, right? So it doesn't necessarily, this is 1 carbon, 2 carbon, 3 carbon, 4 carbon. If we added up the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, this one just needs 1 more. We see it still has the same formula. So it could be that. Is there any other forms we could get it? 1, 2, 3, 3, 3. So that's I guess those are the only 2 options, this one or the straight chain one. We don't know exactly which one it is, but they're both butanes. Well, they both have the same chemical formula. All right, so butane, C4H10. For every 1 million micromoles, we have 1 mole. Correct? And for every 1 mole of C4H10, we have 12 times 4, 48. Carbon weighs 12, 12 times 4, 48. Hydrogen weighs 1 plus 10, so that's 48 plus 10, 58 grams per mole. So there's 58 grams for every mole. So if we take 0.6 divided by 1,000,000 times 58. So I'm looking at 3.48 times 10 to the 5th minus 5. 3.48 times 10 to the minus 5 mole, or grams of butane. Okay, 457. And they got 3.49 times 10 to the minus 5. So good. All right, so that's that one. 1.45 moles of ammonium carbonate. Okay? Ammonium carbonate, ammonium ion, carbonate ion. Ammonium ion has a +1, carbonate ion has a -2, so that's the formula for ammonium carbonate. We want to know how many grams of NH4,2CO3 grams of ammonium carbonate there will be in this many moles, correct? So we need a relationship between the grams of NH4CO3 and the moles of NH4CO3. Okay? So, how many grams are there per mole? Well, we have 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens, right? 1 carbon, 3 oxygens. So, let's see. 14 times 2, 28. 8 times 1, 8. 1 times 12, 12. 3 times 16, 16, 16, 32, 40. 32 plus 16, 48. So we have 48 plus 12 plus 8 plus 28. So that's 96 grams per mole, approximately. So 96 here times 1.45, 139.2, 457, 139 grams. All right, so we got it. All right, so we're on to 459. Calculate the number of moles of each compound in the following samples. So now we're doing the same thing, but we're solving for moles of that compound. Calcium carbonate. How many grams of it? 21.5 grams. Calcium carbonate, right? Calcium has a +2 charge by looking at the periodic table. Carbonate, we might remember, or it might be you look at the table in page 84. But this has a -2 charge, so it's a 1-to-1 ratio of calcium ions to carbonate ions. All right? And we want to know how many moles of calcium carbonate. All right? So we need the grams of calcium carbonate that there are for every mole. Okay? So calcium, 40. Carbon, 12. 3 oxygens, 48. So we have 160, 170, 180. 180 grams per mole. Is that right? 80, 90, no, 100. What happened? 4 plus 4 is 80. What do I think? 80, so 90, 100, 40, 80, 90, 100. 0, 4, 5, 6, 7, 8, 9. 48, 58, 60, that's 40, 100. 100 grams per mole. So 21.5 divided by 100, and that should be how many moles we have. So we get a fraction of 0.215. And we can always double check in our minds, 0.215. Does that make sense? 0.215, would we have less than a mole? Yeah, because we have fewer grams than there are in the mass of 1 mole, right? So we have less than a mole, we know that. Okay, what time is it now? All right. 459. B, 1.56 nanograms. 1.56 nanograms. .56 nanograms of what? 459 ammonia, NH3. Well, there's 10 to the 9th nanograms for every 1 gram. And then in 1 gram of ammonia, that's 14 for the nitrogen, and then 3 for each hydrogen. So there's 1 for each hydrogen, and there's 3 of them. So that's 17 grams per mole. 17 grams of ammonia for every mole of ammonia. All right, so again, this divided by 10 to the 9th, divided by 17. 1.56 divided by 10 to the 9th, divided by 17. So I'm getting 9.3 sig figs 1/8 times 10 to the minus 11. All right, that's 459A. Wait, did I shoot the wrong one? Oh, we're on 459B. 459B. 9.16 times 10 to the minus 11. All right, good. 459C. 16.8 grams of strontium nitrate. Strontium nitrate. Okay, you can see that we have the same pattern here. We just have to erase the chemicals. And this is going to have to be gone now as well because we don't have nanograms, we have just grams. Right? This is a different chemical. Here we go. So strontium, Sr, and we can look and see what the strontium is in the second column. It's going to have a +2, so nitrate has a -1. So we're going to need 2 of those nitrates for the strontium. How many grams of that stuff do we have? 16.8 grams of strontium nitrate. 16.8. So how many grams are there for every 1 mole of strontium nitrate? All right? And that'll tell us how many moles of strontium nitrate. Okay, so how many grams are there per mole of strontium nitrate? We use the periodic table. Strontium has a mass of 87.6. 87.6 for the strontium. Nitrogen is 14. 14 times 2 is 28. That's for 2 nitrogens. All right, so we're finding the mass of strontium nitrate. 6 oxygens, 96. 2 nitrogens, 28. 1 strontium, 87.6. 96 plus 28.0014 plus 87.6 equals 211.614. 211.614, so we have 16.8 divided by 211.614, and that's 0.0793. Oops. 0.0794. All right, so that is 459. Strontium nitrate, 0.0794. Good, got it. All right, next, after strontium nitrate, what are we missing now? Where are we at? 459. Sodium chromate. Yeah, D. 6.98 micrograms of sodium chromate. So we have micrograms here. Just change this to what? 6.98, yeah, 6.98. 6.98 micrograms. I'll set the whole thing up again so it's not confusing, I guess. Micrograms of, what was it? Sodium chromate, Na2CrO4. Okay. And the question is, how many moles of Na2CrO4 is that? Right? Well, there's a million. Oops, one more 0. Micrograms for every 1 gram. And there are how many grams of Na2CrO4 for every 1 mole of Na2CrO4. Okay? So how many grams of sodium chromate are there per mole of sodium chromate? Well, sodium, 23. 23 times 2 is 46. 2 sodiums. Look on the periodic table there. Oxygen. Oxygen is 16. We have how many oxygen? 4. Oxygen, 16, 16, 32, 32, and 32 are 64. 64, 46, so we have 110 so far. And then chromium, whatever chromium is. Chromium is 51.996. So we have 51.996 plus 110. 464 plus 46. So I'm getting 161.996. 161.996. Okay. 6.98 divided by a million divided by 161.996. So 4.31 times 10 to the minus 8 moles of Na2CrO4 sodium chromate. All right, 459. Let's make sure we got it. .31 times 10 to the minus 8. Good. All right. 461. 461. One sample of calcium carbonate, calcium carbide, contains 0.150 moles of carbon. How many moles and how many grams of calcium are also in the sample? Calcium carbide, CaC2, was once used to make signal flares for ships. Water dripped onto calcium carbide reacts to give acetylene, which burns. We're going to finish up 461 here. One sample of calcium carbide contains 0.150 moles of carbon. How many moles and how many grams of calcium are also in this sample? So we want to know first moles of calcium, all right? And we know that there are 0.150 moles of carbon, 0.150 moles of carbon. And we know that calcium carbide is CaC2, right? So that there's 2 moles of carbon, 2 moles of carbon for every 1 mole of calcium, right? So if I have 0.150 moles of calcium, I'm going to have half as much, or 15 divided by 2. 7.5, 0.075. Let me get out my calculator real quick. .075 moles of calcium, right? All right, so that's how many moles of calcium. And they wanted moles of calcium, so we stopped there, but we could have extended it, and we could have, looking for my eraser here. Where's my eraser? Oh, here it is. We could have extended it to, if I have 0.075 moles of calcium, because we want to know now how many grams of calcium that is, right? So we have grams of calcium on top, moles of calcium down below, 0.075. How many grams are in 1 mole of calcium? Use the periodic table. I have my favorite one right here. Here it is. Calcium, 40.0. 40.1 grams per every mole. So 0.075 times 40, and that will be 3 grams of calcium. All right, so that's 461. Let's just double check we're still okay. Good. All right, and they have 3.01 in there, and it looks like this should be 3 significant digits as well. So this is 0.750. 0.750 times 40.1. Is that what I did? Oh. 0.0750 times 40.1. That'll give us 3.01 grams of calcium. All right, 463. How many moles of nitrogen are in 0.65 moles of ammonium carbonate? We're looking for moles of nitrogen, and we're given 0.650 moles of ammonium carbonate. 0.650 moles. And we have to know what ammonium carbonate is, all right? So ammonium, NH4 ion, right? We're becoming more familiar with that one. And carbonate, CO3. CO3 ion has a minus 2 charge on it. So we're going to need to have 2 ammonium ions for every 1 carbonate ion. All right, so this is how many moles of ammonium carbonate we have. NH4, 2CO3. All right, and the question is how many moles of nitrogen are in that many moles of ammonium carbonate, and then how many grams of this compound supply this much nitrogen. Okay, so if we have 0.650 moles, how many moles of nitrogen is that? How many moles of nitrogen? Well, for every mole of NH4, 2CO3, how many moles of nitrogen are there? Well, in here, for every 1 mole of this, there's 2 nitrogens, right? So there's 2 moles of nitrogen for every 1 mole of that. So we take 0.650 times 2, 0.65 times 2, and we got 1.3 moles of nitrogen. All right? And the question is, the second part of the question is, how many grams of this compound supply this much nitrogen? How many grams of this compound supply this much nitrogen? Therefore, how many grams of NH4,2CO3 are in 0.650 moles? So 0.650 moles of ammonium carbonate. How many grams of NH4,2CO3, or ammonium carbonate, does that represent? So we have grams of ammonium carbonate on top, moles of ammonium carbonate on the bottom. We have to know the molar mass of this, right? I think we did this before. I think it was like 106, but we'll add it up again. 14 times 2 for the nitrogen, because there's 2 nitrogen. 1 times 8, 8 for the hydrogen. 12, so that plus 12 for the 1 carbon, plus 48 for the 3 oxygens, right? So we have 28 plus 8 plus 12 plus 48, 96. I was wrong. It's 96. 96 grams per mole. So that's going to be our 96 here. So we take 96 times 0.650, and that's going to be 62.4 grams of ammonium chloride. 62.4 grams, sorry, ammonium carbonate. All right, that was 465. 465. Oh, what was the question? Oh, no. Oh, no, I was looking wrong. 463. 463. 463. 62.5 grams of ammonium carbonate. Got it. Okay, so we're off by 1 there, but it's probably because we didn't use very many significant figures here. Okay. Now 465. 465. How many kilograms of a fertilizer made of pure ammonium carbonate would be required to supply 1 kilogram of nitrogen to the soil? How many kilograms of NH4,2CO3? NH4,2CO3, right? How many kilograms of that stuff? Right, that's what we're looking for. Kilograms of ammonium carbonate. And we're starting with, we want it to supply what? 1 kilogram of nitrogen. So we want it to supply 1 kilogram of nitrogen. All right? So 1 kilogram of nitrogen, we can convert that to grams of nitrogen if we want to. For every 1 kilogram, we know there's 1,000 grams of nitrogen, right? And then we can convert that nitrogen to moles of nitrogen, right? So for every 14 grams of nitrogen, that's 1 mole of nitrogen, correct? And then we can go to moles of NH4 carbonate. For every 1 mole of nitrogen, or every 2 moles of nitrogen, that's how many moles of nitrogen there are in 1 mole of NH4CO3, NH4,2CO3, right? Finishing up our view problem 465. We wanted 1 kilogram of nitrogen, and we determined how many moles of nitrogen would be in 1 kilogram. And then we said there's 2 moles of nitrogen for every mole of this ammonium carbonate. So we just have to do it in the calculator here. 1 times 1,000 divided by 14 divided by 2, and that's it. So it should be 35.7. 35.7 kilograms of ammonium carbonate would provide that much. Let's see, this is 465. Just make sure we got all that right. How many kilograms of fertilizer made of pure that would apply, required to supply that much nitrogen to cell? 465, 35.7. What? What am I messing up? 1 kilogram of nitrogen, 1,000 grams of nitrogen, 14 grams for every mole, 2 moles for every one of these. That's how many. Oh, I'm not finished.
What is it? What is it?
I'm not finished yet. Okay, so I thought I was done, but I'm in moles of this stuff. So for every 1 mole of NH4CO3
Will be how much grams?
NH4,2CO3, how many grams of NH4,2CO3, and then we also have to get that to kilograms, right? There's 1,000 grams for every 1 kilogram. All right, so nitrogen, 14, you can open that up to wherever it is. 14 plus 14, 2 nitrogens plus 8 plus 1 carbon, 12 plus 48 for the 3 oxygens, 96. So this is 96. So let's try to get 1,000 times 96 divided by 14 divided by 2 divided by 1,000. All right, 3.43. Good. So that's 3.43 kilograms of fertilizer. Excellent. 465.